Hello, today we are going to work on the chain rule, which is a helpful little tool that you will see quite often in high school calculus and beyond if you continue to do math in university or wherever you may end up after high school. So if you've been working on derivatives, these first two derivatives might be familiar to you. You might know how to do them already. For example, this one, the square root of x, if we think of it as x to the power of 1/2, when we take the derivative of it, which I should write that here, taking the derivative of x to the power of 1/2 means we roll down the 1/2, then we subtract 1 from 1/2, we get x to the power of negative 1/2. You could also write this as 1 over 2 root x. So again, that might look familiar, might be used to doing something like that. For this one, similar idea, we're doing the derivative of x to the power of 5 plus 3. So we get 5x to the power of 4, and then our plus 3 goes to 0. So that's if we have like a square root function or an exponential, or if you have something like 2x, the derivative of that would be 2. So that's if we have functions that we're familiar with. What if we have a composite function like we have right here, which is the square root of x to the power of 5 plus 3? What then? So that's where the chain rule comes in handy. And there's a few different ways you might see the chain rule written out. One of which is, for example, you might see like this: f of x is equal to f of g of x, right? And if we're taking the derivative of big F of x, then what we end up getting is the derivative of f of x, which you might see as f prime. So it'd be f prime of g of x, and then you multiply it by the derivative of g of x. So that's what the chain rule is. You can also see it, and you might see this more if you're in university or doing multivariable calculus, but you also might see it just in non-multivariable calculus. So I'll write it down just in case, but this one that you're seeing here is more popular, I think, in high school. So the other version you might see it as if you have y is equal to f of u, where u is a different function of x. In this case, we're saying g of x. Then the derivative of y with respect to x is equal to derivative of y with respect to u times the derivative of u with respect to x. So this is kind of why you can see why it's called the chain rule, because you start at one thing and then you kind of link everything together. You're starting at y, then you do the derivative of u, then the derivative, you just keep going. Again, this second version, I'm not sure how much you see it in high school, but if you are thinking of continuing your studies in math after high school, I would definitely be familiar with this, because I'm studying physics in university, and this is what I see most of the time. But if you're more comfortable with this version, that's totally fine as well. Or, sorry, that format, that's totally fine. They both say the same thing. So recap, what we're looking at is if we have a composite function, f of g of x, and you can keep going, you can do f of g of h of x, and just keep piling it on. The derivative of that is equal to f prime of g of x times g prime of x. And I will add, like I said, with the chain rule, you just keep going with the functions that are inside each other. Technically, and we don't write this out because it's kind of redundant, but technically, and I'll do this in a different color, we're also multiplying it by x prime. However, x prime is saying the derivative of x with respect to x. That's what this is. And that's just equal to 1. So we don't write that part out because it's just equal to 1. But technically, that is what we're doing. And I'll show you how this relates the chain rule to all of the derivatives that you'll do, regardless of if you think you're doing the chain rule or not. So let's go back to this original example that I came up with here, the square root of x to the power of 5 plus 3. How are we going to do this? So the first thing I would do is recognize or come up with the two functions that we think we're looking at. So our f of x and our g of x. So if this is equal to, let me pick a different color here. If this is equal to f of g of x, okay, and we know it's in terms of x because that's what we have in our derivative and in our function, g of x is equal to x to the 5 plus 3, and f of x is equal to the square root of x. Now, this is where using that u instead is kind of helpful, because if we're writing this out as two different functions, I've used x twice, which can be kind of confusing. So the other way you could write this is write it like f of u, and the square root of u is our first function, and then we would say that our inside function, u, is equal to g of x, which is x to the 5 plus 3. Now, this is, in my personal opinion, I prefer to do it this way because then we're not reusing the same variables. But if you find it less confusing to use the same variable twice and say f of x and g of x, that's totally fine. I'm going to write it out this way because I think it's good to know both ways to do it. And it's all really notation, so it's whatever you're most comfortable with. So you can try different ways, and you might see more than one way in your textbooks and on tests and whatnot. So it's good to be familiar with more than one way to do it. So if we follow what the chain rule is telling us to do, then the derivative of our overall function, which I could call big F of x, is equal to f prime of g of x times g prime of x. Okay? So looking at our f prime, if we're talking about f prime of u is equal to, well, we're taking the derivative of square root of u, which is 1/2 times u to the power of -1/2. Okay? So that is the derivative of f. Our derivative of g of x is equal to, taking the derivative of this, is equal to, should probably write that out, 5x to the power of 4 plus 0. Okay? And so we know that our overall derivative is equal to these two things multiplied together, as I've got written down here. So if I multiply them together, then I get 1/2 u to the power of -1/2 times 5x to the power of 4. Now, the only thing here is I have this u, which is kind of clunky. Not great because we're trying to look at in terms of x, but we know what u is. U is equal to that innermost function. So this is equal to 1/2 g of x, which is equal to x to the power of 5 plus 3 to the power of -1/2 times 5x to the power of 4. Now we can clean this up a little bit. This isn't the prettiest way to see this function. So writing this out a little bit nicer, the derivative, not ddr, that's not correct, ddx of the square root of x to the power of 5 plus 3 is equal to 5x to the power of 4 divided by 2 square root x to the 5 plus 3. So that is the whole chain rule. And you can do this with all different types of functions. So the one that I've done here is with a square root and another function inside of it. It's also really common to use these for trig functions. So let's just do a quick example of that. So if I have, let's say, the function sine of, I don't know, let's say x to the power, let's say 3x to the power of 2. Okay, so this is, we know that we can find the derivative of sine, and we know we can find the derivative of 3x to the power of 2. So fuzz there. So the derivative of sine x, that's not what I want to say. Ignore that, I just said the derivative of sine x. I'm backtracking. We're going to have to cut that part out. My apologies. So I'm just going to start from the trig example from the beginning. So ignore the trig stuff. We're going to start from the beginning there. So if we do an example with trig, let's try sine 3x to the power of 2, and we're going to find the derivative with respect to x. So in this case, my outer function, f, I'm going to call it f of u again, is equal to sine u. And my inner function, which I'm going to call g of x, is equal to 3x squared. And remember, we're thinking that this overall function, sine 3x squared, is big F of x. So when we take the derivative of big F of x, which I guess I should be calling it capital F, big F of x is equal to f prime of u, which is g of x times g prime of x. Okay? So if we do this, that is equal to the derivative of sine is equal to cos. So we get cos of u times, that would be 6x. And then all we have to do is plug u back in. And as we know, u is equal to g of x. So this would be equal to cos of 3x squared times 6x. And that is the derivative of sine 3x squared. Okay, should be a D. Okay, so one last thing before we go is, as I mentioned, when you're doing this, you're technically also doing multiplying it by dx ddx of x, which is equal to 1. So as we're doing this, this is technically also being multiplied by 1 every time. So this is why I mentioned that anytime you're doing a derivative, you're also doing the chain rule. And I'll just show you that really quickly here. So let's say we have the function 2x, and I want to find the derivative of 2x, right? So the derivative of 2x is equal to, and I'll write an equal sign there instead, is equal to 2. But I'm also doing the chain rule and multiplying it by the derivative of x, which is just equal to 1. So it's equal to 2. So you don't really see it all the time, but every time you're doing a derivative, your innermost function is x, but every time we take the derivative of x with respect to x, it's just equal to 1. So that is technically what you're doing every time, we just don't see it. So that is an overview of the chain rule. Like I mentioned, being familiar with both of these forms can be very helpful. But in general, if you understand what I've got between these blue brackets here, regardless of, let me just put a little wiggly line there, which version you like better, you should be good to go. And you can do this with any functions, any composite function, you can use the chain rule to take the derivative. So hopefully that makes sense and gives you a bit of a head start with using the chain rule.